We're going to look at safety, and y'all are responsible for these chapters, right? I don't have any idea what this is. The chapter 3 deals with electrical safety first. PPE, most people call it PPE, but this is personal protective equipment. Lockout, tag out, which we're going to do this semester. Lockout devices, and a little bit about fire safety. We're going to stop about here. Let y'all come in and read this on your own, because we're not going to have to deal with any of that in this class. First of all, a lot of this information is inside the National Electrical Code. Is the National Electrical Code, is that law? Is that the law? Is that the law? No. What the National Electrical Code is, it's recommendations. Yeah. It's up to the authority having jurisdiction. So whoever's over, so the electrical inspectors for Jefferson County, they decide whether they're going to adopt the National Electrical Code or if they're not going to adopt the National Electrical Code. And the National Electrical Code comes out with a new revision every 3 years. But it usually takes about a year before the authority having jurisdiction to adopt the new code because they got to go through it, right? They have to understand it. And they update this every year, but it's not law. OSHA is law, but NEC is not. And you'll see, and does the National Electrical Code, is it written to protect you? No. It's written to prevent fires. In fact, the National Electrical Code is written by the National Fire Protection Association, NEC. It's in there to protect equipment. It's in there to prevent fires. It's in there saying, okay, if I wire this correctly and I do things right, then there's an extremely high probability that I won't have a fire unless somebody actually comes in and screws up. And of course, what happened was they realized that there was really no safety except for OSHA, regional safety. So National Fire Protection Association came out with. So the actual NEC is actually standard 70. That's NEC. That's their code. That's the code. That's it. We call it the National Electrical Code. Now everybody here adopts it, but you might live out in the county somewhere and nobody has jurisdiction. But I highly recommend that you wire it according to the code, right? And if you own a house, you don't have to have it inspected. You can do anything to your house you want to, right? You understand? It's just that if you don't wire something right and it burns down, and then your insurance company comes in and finds out that you didn't do something right, then they might not do what? They might not pay for your house. What they did though is they came out with a safety standard. It's most people just call it 70E. If you ever heard of that? That is protecting you. So this is the thing that the employer has to do to protect your safety from electrical shock. OSHA covers all kinds of stuff. OSHA has just about any job you can go out and work. Whether you pick up a screwdriver or something, there's probably an OSHA rule and regulation that says that. The problem is that a lot of companies are not under OSHA. You have to be under OSHA, you have to do interstate commerce, which means you got to sell your product across the state line. If you sell your product across the state line, then your company becomes under OSHA. But odds are, if you're in a place and you get hurt, whether it's at a grocery store, which is probably not covered by OSHA, if you get hurt in there and it's the employer's fault, then you got legal grounds for a suit, right? You understand? And a lot of employees when you go to work, the first thing you're going to do, it usually takes at least a week, is to go through safety training for that, company. And a big portion that you have is NAFTA 70E. This determines what you need to do to avoid getting shocked. And then, of course, protect yourself between arc, what we call arc flash, and then arc blast. So it's not in there to keep you from getting electrocuted. It's in there. The rules that they put in there is in there to guarantee the employer puts you in a safe situation where you're going to get shocked. Because you can't get electrocuted unless you get what? Shocked. So we don't want to get shocked. We don't want to get shocked in the first place. So these are just nameplates, and we'll get into nameplates later on. Warning labels. Probably see these all over the place. Different colors mean different things. So red usually means it's what? Now what's a hazard?
Hazard is like if you have a gas can.
Yeah, but that's what we're trying to do is what is a hazard. We're not saying give me an example of a hazard. We're saying what is a hazard. It's something that has the potential of causing injury, right? It don't mean it's going to injure you, but it has the potential to cause that. So dangers mean there's a high probability that that hazard could cause problems, right? Warnings is just like there's a potential that hazard could cause. And then of course the caution is just telling you to look out for stuff, right? And then over here, this is the symbol. And this is blown up a lot better. Y'all can see that. This is in the book. So y'all get it. Are you okay? Electrical shock. So this chart gives us a basic layout. This is what the book teaches right here. And I've got it. The problem we have with electricity, number one, is that all our muscles are controlled by electrical current, right? And if we get into electrical current that overrides what our brain can put out, then we can have problems as far as it's getting stuck in we call it getting stuck in a circuit. So when we start looking at this chart, it says, okay, so down in here, from 0 to milliamps, you can't even watch. And we do this all the time. Then between 1 milliamp and 5 milliamps, these are still, you'll be able to feel it, but these are considered to be what? Safe value. Anywhere between 15 to 20, then this is a painful shock, but we might get the ability. Now we get more current running through our bodies, and our brain can't do things with it anymore, right? So it can't control our muscles, so we might have a tendency to do what? Yeah. The problem is when we get locked onto something, we get nervous, we start sweating, and our body resistance drops down a lot. So that gets you in trouble. Anything above 28 milliamps could be considered to be legal. But they say 50 milliamps is definitely legal for your heart convulsions. Normally we say fibrillation. The heart goes into fibrillation. The problem is, and this is where AC becomes more dangerous than DC. Because AC, the pulses are occurring 60 times a second. And your heart's beating about 60 times. Mine beats around between 60 and 70 times a minute when I'm not doing a minute. And then I bring in AC and it's trying to make it beat at 60 times a second, and your hearts can't keep up to it. And your heart will go into what we call fibrillation. You know what that is? Yeah, but it's when your valves and your heartbeat are no longer in sync with each other. So your valves are opening when they're supposed to be closed, and you're not generating any blood pressure. And that's real bad, right? And what's something is they use a shock to get you back into sync. You know, they use it's just one pulse, right? And it pulses everything to try to get your heart back in. And then we get up here into these guys. These are real bad. Current in a 100-watt light bulb can electrocute 20 individuals. So a 100-watt light bulb running off 120 volts. And it's a resistive load. It don't have any shift in it. Where's my pen at? So I is equals P over V. So that's a 110 watt bulb, right? I mean, it's a 100 watt bulb. And we run that on 120 volts. How much current would that be? What's that? About 80 something. That's so.
83.
Yeah. So the current that lights up that big old bright 100 watt light bulb, and these are incandescent. We're not talking about these LEDs. These guys, you need to look. It says it's equivalent light. So you get an LED bulb and it says equivalent light, and you need to look on down and see how much power that thing. Now, what determines how much current flows through your body? The resistance, well, the current's what yeah, so I is equal to what? V over R. So this is why the higher the voltage you get into, the more dangerous it is. And it also depends on how much current flow, how much resistance you have in your body at a time. I got a diagram, I need to find it in this class. But between your ears is only around a couple hundred ohms, guys. So if you got shot between your ears, you do. So it all depends on path. Two of the most dangerous paths are the ones that will take current flow to your heart. So that would be hand to hand, right? You understand? From this hand to it's like from your right hand to your left leg, or vice versa. Any of those paths will take it to your heart. If it goes through your heart, then you got problems. The higher your voltage you get into, what happens is it tries to take the least resistance path through your body. Unfortunately, it's through the bone marrow through your bone marrow. It kills all that marrow in your bone, then you're really in trouble, right? So, we're not doing this to scare you. I mean, there's, of course, they just came out with a report that says more people are getting killed by drugs now than opioids than there are by car accidents. So there's a lot more people killed in car accidents and all that. There's probably, So you're in a trade that has the potential of being dangerous. But if you take care of yourself, it's not as dangerous as getting in that dang car out there and driving home every day. And that's the aspect you better look at. It's a trade, but if you take the time, don't get in a hurry, make sure you know what you're doing, make sure you know what voltages you're getting into before you do anything, then you're going to be okay. If you're the kind of person that wants to do it now, we got a video, I think I'll find it. It's a tribute to a guy, his name is Eddie. So Mr. Sanders says in this class too, but it's a tribute to him. He got electrocuted. And they was having a problem with something not working, and Eddie went running into this high voltage switch station by himself, which is illegal. Got in there and used the wrong type of meter to measure that. Yeah. Used the wrong meter to measure it, and his meter blew up and it had a big arc flash and just caught him on fire. And people was back up here and they were looking and they saw this fire moving back behind the building there, and they didn't realize it was Eddie out there trying to walk around.
Oh, man.
Eddie didn't make it. So number one, he didn't have on the correct PPE. He's working on 2300 volts. He should have had on almost a blast suit before he went in there. Number two, he went in there by himself. Out at US Steel, our limit was 500 volts. If we worked on anything above 500 volts, we had to have somebody work with us. But I never at US Steel went on a call without two people. They always sent two people. And then the third thing he did, he knew he was using a meter that wasn't rated at the 2300 volts that he was trying to measure. So when we got in there and created that arc, as soon as he created that arc, it created what we call ozone. Ozone has a very low resistance, and then then things start blowing up. And we called it an arc blast, which is not good. But the problem with an arc blast is it comes out flying out. Arc blast is hotter than the sun. It's like 32,000 degrees coming flying, or 3,200 degrees coming flying out at you. And it hits you in the chest. What's the first thing you do? Right? and all this garbage is flying at you, all this vaporized metal and all this other stuff's flying at you, and you inhale that stuff, and that's where you really get in trouble. But if he had followed the rules that he should have followed, Eddie would probably still be around today, right? Of course, it don't mean you're going to be totally safe. We tell people, if you follow the traffic rules, there's a high probability. If you stop at every red light, there's a high probability. If you never stop at a red light, you're going to have a wreck. Right? You understand? So if you break safety rules all the time, you're going to have a problem, right? You understand? Just because you follow all the rules, though, don't mean that somebody's not going to rear end you. So that just, things like that happen. It's just that you a lot of probability. Grounding. So what we do is we have two conductors, at least two conductors. We might have three or four, depending on whether it's a three-phase, grounded three-phase. We call it delta. Grounded would be a Y. Delta would be ungrounded three-phase. And then we have single phase, which is what we're used to. And, we're going to be dealing with both of them here. So coming out of our disconnect, we're going to have three-phase there. And then it's a 208, and we're going to run it through a transformer, and we're going to step it down to 120 volts. It's not actually 120 volts, because it divides up to 10. Now, what we do is, in most wiring, is we run, especially single phase, we run two wires. One of them the electricians call, what do they call them? Anybody know? Electricians. They don't call them red. They call them hot and neutral. So what's the difference between the hot and what's the difference between the neutral? No, neutral is. The ground is not.
Yeah.
Neutral is supposed to carry current.
Yeah, neutral is a return current.
Well, you can't really say that. It's AC. AC has no return. Yeah. So sometimes the hot is the return conductor, and sometimes the neutral is the return conductor because the polarity is constantly changing. So we call it common. It's a common conductor. But in house wiring, and also a lot of any single phase wiring, and even on three phase, we use a ground. So we have three wires. We have two that carry current, and then we have one that's not supposed to carry current. The only time it's supposed to carry current is if there's a problem. And that's going to be what we call our grounded conductor, right? Now, the problem we have is that, first of all, anytime I push electromagnetic waves through a chunk of metal, it's going to induce voltage into it. Y'all know that, right? We proved that over here. So 90% of our current is probably in transmission. It's AC. So if I've got a metal cabinet and I've got AC inside of it, if I didn't do something, it would build up a charge automatically relative to ground. So that means you'd walk up on it and you'd touch it and it would shock. So what they do is everything metal has to be connected to ground. So if something connected to earth ground, that is the common for all most AC being generated, then there's no way in the world that metal chassis could pick up a static voltage, right, or a static charge. Another thing is that we got these metal cabinets, and I bring two wires in it, and I don't reference it to anything, and something happens, and the wire shaves, and that black lead gets on the outside metal of your thing, and you've got instead of that metal cabinet on your refrigerator being a cabinet, it's going to be a conductor now, right? You understand that? So what we need to do is figure out some way where we could prevent any metal thing from becoming electrically hot or electrically charged. So what we do is we ground the neutral. So the neutral inside your panel box is connected to earth ground. So NEC calls it the grounded current carrying conductor. So the neutral carries current. Then they call what we call the hot leg, they call that the ungrounded current carrying conductor. So if something happens and your neutral gets up against the chassis of your car and wears out or something, I mean not your car, your house, it's not going to be any difference because it's grounded anyway. right to understand. But if that hot leg gets up and touches or somehow touches the chassis of your refrigerator, then it's going to, now we're going to have current in the ground, and it's going to be a short circuit, and what would it do? Should pop your breaker, right? You understand? But you could literally take that ground and you could cut it off and your refrigerator would run fine. But now you've lost your what? You've lost your protection against the chassis of that thing becoming electrically hot. So with that ground connector in there, it says, okay, if that chassis becomes electrically hot, it can't because it's going to go back to ground, right? In your neutral reference ground. So we ground for safety. So the ground's in there for safety. It prevents any chunk of metal that you touch from becoming what? Electrically hot or electrically solid. Of course, we have what we call double insulated tools, and these are the tools that the cases are plastic. So the cases are plastic, which means you don't have to have a lot. A lot of times the plugs are polarized. You ever notice the plugs, the 120 volt plug? It's got blades on it. Have you ever noticed something? One of them's bigger than the other one. Does that mean anything? This is supposed to be the neutral. And then this is supposed to be what they call hot. So a lot of times you'll get that they use a polarized plug. They just want to make sure you plug. Are you okay? So grounding provides a direct path for unwanted fault current to earth ground without causing harm to the individual and equipment. So if I ground the frame of this guy right here, and then one of these hot leads, even if it's 3-phase, somehow gets in contact with this metal thing, it's going to trip your overcurrent protection device. And what's our two overcurrent protection devices primarily? Fuses and circuit breakers. I think you can buy these extension cords that are unpolarized. Those things are dangerous. So, y'all probably, if you've been in my class before, you heard this story. My wife's grandmother, she had a son who came in and they needed to run an extension cord to her refrigerator. He went out and bought an unpolarized plug, cut the ground off her refrigerator plug and plugged it in. The refrigerator came up and ran fine. She got in there one day and she was leaning over to open her oven and her rear end hit her refrigerator and it zapped her. Because now he plugged the thing in backwards. And I came in there and I unplugged it. I said it's dangerous, we need to have it grounded. But I just pulled it out of the wall and turned around and plugged it in. And he said, well, that won't make any difference, it's AC. I said, yeah, but one of them is what? And one of them's hot. So he turned it around. There was no ground on the chassis of the refrigerator, so it didn't do what? Because he cut the ground plug off and it wouldn't pop, right? Because he lost that safety. My father-in-law, he used the ground lead. He needed 120 volts AC, and he used the ground as one of his conductors. I feel sorry for whoever bought that house, but he did. So this is a GFCI. We talked a little about this. So what it does, if both your current carrying conductors, if the two currents match, then this guy right here, this is just a little current transformer, the magnetic fields cancel each other out. So when current's going one way, it would generate maybe a magnetic field coming in. This would generate one coming out, and they just cancel each other out, right? You understand that? So what a GFCI does, it looks for a mismatch between the current in your hot lead and in your neutral lead. Because if these currents don't match, it means that other current's going somewhere else, right? And it's usually probably 99% of the time it's going through something to ground. That's all the secret. So what I can do is I can look for a mismatch of 10 milliamps. So I can put 50 amps through the neutral and the hot, but if I get a 10 milliamp mismatch between my two conductors, then it'll trip your ground fault. Ground faults do not prevent you from getting electrocuted if you get across these two leads right here. If you get across these two leads right here, guys, it's going to think you're a light bulb. It's going to light you up. But if you was to get between this one and this one, then your ground fault would trip out. So don't think the ground fault protects you, right? You understand? Because if you get across your hot and the neutral, it thinks you're a load, right? You understand? So you still got to be careful. When taking measurements in electrical circuit, transit voltage can cause electrical shock and or damage to the equipment. One thing about transit voltage is not actually there. We have a problem with AC2. We call them ghost voltages. Ghost voltages means your meter will measure something when it's not actually there. Because AC wants to induce voltages into everything, right? You understand? So your meter leads, you got your meter leads up there, and you bring it up to an AC circuit. It sees that magnetic field comes in, inducing the voltage into your meter leads. Your meter's got like 10 meg ohms of worth of resistance coming in on the volt scale. So it don't take much to load that stuff. You don't load anything down. We don't have that problem on DC, and some of y'all are going to see that. You're going to see what they refer to as a ghost voltage. So very seldom do you measure zero in an AC circuit. It might be 1, 2 volts. You know, you're supposed to have 120 and you're measuring 5 volts, right? You understand? If you get your meter, then 5 volts wouldn't hurt you anyway, but odds are it's going to be what we call a ghost voltage. If you was to load it, it would go away. Protect the personal technical equipment, PPE, what you're going to have to do. What 70E does, it identifies what they call a arc boundaries. And depending on how, they got all this math formula and everything. So now if you go into a building or a maintenance facility that is covered by where they do 70E, you'll see these lines on the floor in front of switchgear and stuff like that. And what that identifies, and this is what you'll get to on your safety training and you better, is how much PPE you have the closer you get to the danger. Right? You understand that? Personal protective equipment. This guy's dealing with what? He's got insulated gloves on. He's got his hard hat on. Safety glasses. They have earplugs. He's working in the industry. We're not going to require that. So what are we going to require? Safety glasses and then gloves and then of course Cat 3 measure. Because we're dealing with 3-phase, right? The other slide I have is better than this. And what happens is the further you get into it, the more stuff you have to wear. And what 70E identifies is exactly what PPE is required as you move into the thing. Let me bring that up. Well, that's actually a lot better slide. Yeah. Okay. I know Austin. What's your name? Rosa. I got you. I got you, Gilbert. Williams? No. Green. And I know Tyler. Yeah, it usually takes me around the first test before I can start getting held down. Don't worry about that. Here's the one that shows the path. This is the one that shows you the resistance for different portions of your body, which is pretty neat. What surprised me is that
women have a lower threshold than
and don't ask me why.
men.
Of course, like we said, 70E covers against shock, arc blasts, and arc flash and arc blast. And this is what they do. What they do is when they calculate it, they come up with something called calories per centimeter squared. This number right here determines what PPE you have to wear. And this is the different calories right here. The boundaries that you would go through. And then the different PPE. So we're actually below this, but this is pretty standard for dang it. So this is a PowerPoint right out of a 70E standard, and we also have the 1910, which is OSHA. So these are the different color codes, by the way, that they have to color code different things. So now your PPE is going to be color coded depending on. So here's we're below this, but we should be wearing what? Hard hat, safety glasses, and then leather shoes, right? And hearing protection, and leather insulation. This is a 1.4 to 4 calories per centimeter square. Now we're used to what go on. Hard hat, safety glasses, arc rated face shields, hearing protection, voltage rated gloves, leather gloves, and then leather boots. This is 4 to 8, and this is what your gosh. This looks the same, but you got to have an 8+ calorie long sleeve shirt. So you have to start going into fiery clothing, right? Hard hat, safety glasses, arc rated face shields, hearing protection. Voltage rated gloves, which means your gloves have to be rated for whatever voltage you're going to be working in, or the highest voltage you're going to be working in. This is 825, category 3. 25+ flash suit with hood over long sleeve shirt and long pants, safety glasses, arc rated flash shield. Hearing protection, voltage rated gloves, which would be undergear, and then you have to wear leather gloves on top of that, and then you have to wear leather boots. And then this is 25 to 40 calories, 40 plus flash suit rated with hood over fire rated long sleeve shirt and long pants, safety glasses, arc rated face shield, hearing protection inserts. So they don't want you to wear the we call them Mickey Mouse ears. They want you to wear the one actually gloves, yeah. Voltage rated gloves, which are these guys for what you're going to work in, and you got to wear the leather gloves on top of that and leather boots. So depending on this, and there's guys that specialize with coming into your plant. It deals on how close are you to a power source, how many transformers you got to come through, what the rating on the circuit breakers or the circuit is. And it's a lot of math involved to figure out what boundaries you need to go. And then that would depend on which boundary. So there's like 3 boundaries that they go through. It's 3 boundaries that you go through. As you move toward the prohibited, this is where you have your maximum PPE on. If you're back here, you could get into this boundary and not have as much on. This boundary, and then out here, you could be walking around in pants and sandals if you're something around that. This is all defined by NAFTA 70E. Now, NAFTA did such a good job that a lot of this has been imported into OSHA. So there's a lot of stuff in the National Electrical Code that's in OSHA, in the 19 OSHA standard, which is workplace safety. And there's also a lot of stuff that's in the 70E. The 70E is not law. It's recommendations. It's up to your company where you go to work with, or if you're going to follow 70E. Just about every major company that I know of around here now, this is the guy they're looking at now because it does so well. And if you do what 70E says, then you're as an employer, you're going to be okay. Hopefully y'all will work on one of those things where you got to get in your bomb suit, right? From what I've never worked a job that did that. I understand they're very hot. The breakers that they have in industry are so big. And what they do is it's called racking a breaker. So when you install a breaker, you rack it, and basically it's a big old square. It's got all the stuff in there that gives you the breaker. You set it on a set of rails, and then you wind it in, and as it gets up into the back, as the carriage gets up in the back, it actually inserts itself into the high voltage high current. And I don't think I'm not going to hook up the speakers. So this guy, for one thing, just about all your breakers has this hole right in there. So you place the breaker on the rack, you close the door, you latch it, and you rack it outside the door. You can see what this guy's doing? He's got the door open, and he's racking the breaker, so he's got a thing, and he's turning. And you probably noticed he got his, he should probably have more PPE on than he's got. He don't even have his face shield on. You see him turning the thing?
What other guy? He in there too?
He is, but he leaves before the thing. But what's happened is something's happened with the back of the breaker where the blades that go in are not quite right. And then it creates a short. And there's so much energy inside this cabinet that it creates an arc flash. And then the arc flash creates an arc lamp. So he's safe now. If it had stayed in there. You'll see him put his face shield down here in a second. He did. So that's an arc flash, but that flash created what we call an arc blast.
He did. He made it.
It would surprise me if he would, because he didn't have on the correct PPE to start off with, right? You understand? And then plus, he was not doing it right. So that's what that hole in that door is. So normally it looks like a crank handle, right? You understand that? And what they're supposed to do is once they get it up on the rails is do what? Close the door, latch it down, and then stick that thing in there and rack it from the outside.
He's already wrong with having a door.
Yeah. Now, if he got into an old panel, it might not have that, but all your new panels are going to have that. Yeah, but if he had a face shield on, when it hit him, he wouldn't have went like that, right? You understand? He'd have went that, but he wouldn't have sucked that stuff in. And it would have knocked him out. He might have broke. It's like a bulletproof vest. I wouldn't want to do that, but just because you get a bulletproof vest, well, if a bullet hits you and you got the vest on, it's going to knock your butt down, right? You understand? And it's going to bruise you, and it might break ribs, but at least you're what? Yeah, you're alive. So it's not going to say he's not going to get hurt, but there's a high probability that he won't get killed. But it don't mean he's not going to get killed. So even if he had it on and it knocked him back and he fell down and bopped his head on something, but it would be a higher probability that he wouldn't.
That's why they required every certain time to replace your gloves and.
Yeah, you have to have them checked. There was a place over on Lime Avenue. I forgot the name of the place, and that was one of the things they did. They checked the gloves. You'd have to bring them in every once in a while, And what they'd do is they put it in a charged material and they'd fill the inside up and fill the outside up and put 2 electrodes in there and dump them down. And if you got so much current flow through the gloves, they would throw them away. And if you got any of these rubber gloves we usually don't work with rubber gloves. Usually they have rubber gloves because rubber's a real good insulator, and then they'll put leather gloves on top of it. And then they'll check those things when they put them on to make sure the rubber gloves have no holes in them or anything like that. So most of the people that get electrocuted, it's their fault that happens to them. I'm sure there are accidents somewhere. It's just like I said, driving a car. You could honor every safety rule and every speed limit and all, but it doesn't guarantee somebody's not going to T-bone you, right? You understand that? Or run into the rear end. But there's a higher probability if you never follow any of the safety rules, if you always run red lights, then it's not if you're going to have a wreck, it's when you're going to have a wreck, right? Are we okay? So I'm going to get out of this trade. But like I said, you're more likely to get out of here today in this class and go out there and get in that car and have an accident than if you follow the rules with electricity and get electrocuted. If you look at the number of people that gets electrocuted every year compared to the people that gets killed in wrecks, you'd see that it's very, very low. Relative. It's just like plane crashes, flying in planes is one of the safest modes of transportation there is out there. But when a plane crashes, it usually kills quite a few people. So. I'm sure I'm the right one. Nope, I want it. So what's lockout, tagout? Now that's the trick. It's a method of removing the power source off a piece of equipment. Now we can do that, but lockout tagout is a method that prevents other people from energizing a power source. Right? You understand? So I can go in my house and I can click a breaker. That's not lockout tagout. Right? Understand? So I could be in there working and somebody come in there. We didn't do lockout tagout when we was in the service. When we worked on these airplanes, and they had what we call a load cell. It was a big airplane. It was a P-3 Orion. It had all your switching and all your relay was behind the door, and it was a little panel. We had a guy called Tex. He killed power on the plane, and he was in there replacing one of these high-powered relays. And while he was in there, somebody put power on the plane. And Tex had his screwdriver stuck all down in there. And it melted that screwdriver. It was so funny. He didn't get shocked, but it sure scared him. But there was really no way you could lock it, but we should have gotten a technique of tagging. So locking is a method of preventing other people or other individuals from turning a power source on. What's the tag? Well, it's purveying information. So you can have a tag without a lock. So in this situation, if we don't have the ability to lock something out, then you should put a tag on there telling people don't energize this source, right? So there are some situations where you cannot lock out and you cannot lock because it's just not available to you, right? But definitely anytime you put a lock, you should have a tag. But you can have a tag without a lock. So they are not the same. So what information should we put on a tag? Who put the lock on there, right? Depends. What you need to do as a minimum, you should have who put the lock on there. And then you should probably have some method that they could get in contact with you. Is it okay for somebody else to take your lock off? Can it be done?
Yes.
What do you have to do though? You have to exhaust every possible means for contacting the person. You can do it, right? You understand that? It's usually a supervisory provision. You cut it off if you don't have the key, and normally you don't. When we worked at U.S. Steel, from what I understand, when we worked at U.S. Steel, the supervisor had a key and we had a key, and they had a lockbox that they only had a key to. And then what they would do is they would put their key in there with your name on there. And that way, if something happened and they had to take your lock off, first of all, they got to try to get in contact with you to see if it's okay. But if they exhaust every means, so you're over there 6 feet under and they can't take your lock out right off, then y'all understand that would really be a problem. So if you're passed away, then sure, they can take that lock off because there's no way in the world they can contact you, right? But they got to usually they have to fill out a form saying, okay, we're taking this guy's lock off and this is why we're taking it off and how many means you tried to get in contact with this person. But normally that don't happen. So normally the way things should work normally is that whoever puts the lock on should be the same person that takes it off. Everybody okay there? And if you're working with 3 people, how many locks should you put on there? 3. Everybody that's working on the assembly should put a lock on it, and they should put a tag. So what we're going to do is I'm going to be the lockout, but you're going to tag out. So all of y'all that's working in a team is going to have a tag. And anytime you're actually working on that thing or got a work in progress, so the way this is set up, your team is going to be assigned one of these white triangles. So that means there's really no meeting to say, well, we've only got 30 minutes. We don't have time to start another one. There's nobody that uses these things but you. So what can you do? Well, you can start wiring one up, right? Make sure you keep up with what you're doing. So that way when you come back next class, you don't say, well, I don't remember why I was at, right? Understand? You need to keep up with that. And then you put your tags on there and nobody else has the ability, should come in here and take that tag off, right? Understand? That makes sense? So I come over there, you got your tags on there. The first thing I'm going to ask you to do is probably to take them off because legally I can't turn power on if there's a tag up there. And we'll put our tags up on the disconnect. We're going to use rubber bands too, so it's not true to life, but it's close enough. Just to get you in a habit of doing it. If you get into a place that don't maintenance place and they don't follow lockout, tag out, guys, I'd get me another job. Honestly. So a tag is a sort of card, paper, or metal. So U.S. Steel, we used to use plastic lockout, tag out cards, the big ones. From what I understand, U.S. Steel actually went to brass markers with a number on it. Indicates who placed the tag, the date it was placed, the name of the worker is involved, the supervisor's name, and the work done. It depends. The minimum should be what? The name. Usually how we can contact you. Tags warn that machinery or equipment has been de-energized so work can be safely performed. A tag should be good. Our tags are going to be made out of paper. So our tags, if you mess up your tags, you tear it with you. But you understand why they should be durable, right? Because you're going to use that tag for a long time. This is why they don't use it. Every job I've worked at, they usually don't put the date because all this information is on the tag already. And you're supposed to disconnect and tag every power source. So what other power source do we have besides electricity? We'll run into it in the future. Hydraulic or pneumatic. The problem with hydraulic and pneumatic is they have, not only are they energy sources, especially pneumatic. Pneumatic stores a charge, right? You understand that? So one of the things you're supposed to do is you're supposed to bleed off or all the kinetic, all the, what they call it, potential energy. So you got a piece of equipment up here in the air, and if you turn power, it's going to drop. But what you're supposed to do is get it down or chain it up. So that's mechanical stored energy, right? So anything that's supposed to have stored energy, you're supposed to bleed off that stored energy if possible, or do what, or make it safe. So if you got something that's going to fall when you turn off electric power, you need to do what? You need to chain it up or rope it up or something like that, right? You know what I'm saying? That would be considered stored energy. We had, and people got hurt at U.S. Steel all the time. When I worked out there, all the mills were going when I worked out there. And there was 10,000 people that worked at all the mills out there. And they were basically killing one a month when I worked out there. But there's one guy got out there and he was working on a motor. And he had one of these big old torque wrenches, about that big. And he was out there torquing it down. When they changed shifts, so when they changed shifts, nobody told them that this guy was out there. So the first thing they do when they come in is they jog the motor. Jogging motors means you go out there and you just hit them in a burst of position stuff and stuff like that. And they came in and jogged the motor, and that big old wrench they got on there, like to beat him to death. It broke both of his arms. And this is a true story. If you get a lost time energy, your workman's comp goes up. So if they could get these people out there to that plant, they would meet them at the gate with one of the inside ambulances. They would load them in that ambulances and they would take them somewhere and keep them there for their 8-hour shift. So they wouldn't get any lost time accident because of an accident. Because it was cheaper for U.S. Steel to do it that way than to do what? Document it as a job energy. Yeah, so that was more than happened at morning. Well, yeah, and plus it'll make their workman's comp go up a lot, you know, so that's a true story. I forgot one guy had his leg broken. He played video games all day.
Yeah, it worked.
Yeah, it worked. They put him in one of the boss's office and he'd sit there and play video games all day. Well, old leg and a calf. I forgot. I don't know. I can't remember how he broke his leg, but so I know of 2 instances where they brought people out and brought them on.
You remember I had that workers' comp last year. I had your PLC class, and they still made me come to work for like 3 or 4 weeks, and I had a broke arm. I fell off the dock at UTN, and I tore up my arm real bad. I was still in their phone box. It took like
they made you work.
Oh yeah, they made me work about 6 weeks until you know how like long and process the workers' comp is. Like 6 weeks until I finally went to surgery. Yeah, I'll fill in the phone box.
Lockout tag out procedures, proper planning, notification of all personnel. They say the actual thing says all affected personnel. So everybody that works inside your area, operators and anybody that's going to be in there, you need to let them know. Shutdown of operating controls, isolation of all energy sources. Lockout, tag out, the isolate device. Release all what? Stored or residual energy. So sometimes it's misleading. Like I said, you got something up in the air, and when you kill power, it's going to fall. And that's stored energy, right? You understand? You have to do something to keep all that stuff. Verification of isolation of energy. This means even if I come out there, somehow I'm going to verify that energy is no longer available. You don't want to depend on a contact inside a relay de-energizing your power. So how would we check to see if our lockout tag out's working? We use a circle of V. We use a voltmeter. So every time you turn that thing off, you put your tag up there. Before you get your hands up in there, you're gonna get your voltmeter out and measure that three-phase over there to make sure it's close to zero. Odds are it's not going to measure zero because it's AC, right? Understand? And like I said, it's very seldom on an AC circuit that you read zero on your meter. Just strictly because it's what? It's AC. And it's got that change in magnetic field, even though it's not out there, it's inside your disconnect. And it's all over here. These guys, these fluorescent lights are awful about electromagnetic interference if they're not shielded correctly. So we're going to kind of do lockout, tag out. Y'all are going to do the tag out, and I'll do the lockout. In fact, when we put power on, you'll see me take the key, turn it, pull it out, and then I'll turn it back to the left position. So what that means is, as soon as you hit that E-stop button, it is locked out. So I don't have to come over and put a lock on there. So I put it in a position that it will automatically lock it out, right? You know, push the button. But I always verify to make sure. Once you take off the tag, once you put your tag on there and lock, and that button's pressed, right? What are you going to do? Going to verify it. Everybody okay? Any questions? Of course, over there in when we do, if you take the AUT 208 class, it's a troubleshooting class. You hear everybody saying, "I'm fixing to lock this out," but y'all don't have to do that. So that's what you should do, right? When you lock out, you should inform everybody around you that you're locking that out. So any questions on lockout, tag out, guys? Y'all think we'll do okay? So what PPE are we going to require? Safety glasses with side shields, right? So these glasses, you'll see me, I'll put on safety glasses. I won't wear these. These are not safety glasses. These are glasses. I've heard people say that, they say glasses is good. They're not. You can get prescription safety glasses, or you can get clamps that you can get. But while we're looking, you can get safety glasses that go over your glasses if you need them. But glasses are not safety glasses, and we require side shields because something happens over here and it comes in through here, you got problems, right? And then we're going to have some insulated gloves, whether you buy leather gloves or insulated gloves, not insulated knee, insulated gloves. And like I said, all your mechanics gloves are going to be insulated. So if you go over to Harbor Freight and buy a pair of the mechanics gloves that they sell over there, and we're going to try to get into lab sometime next week. So let's go to chapter 3. Nope, wrong class. I really confused y'all. By the way, we're doing the troubleshooting class, which is AUT 208 in T2. And we're going to drop the, originally when we brought the class on board, we envisioned that the students would need sensors before they take it.
You're dropping the sensor class.
Yeah, we're dropping the sensor.
That's awesome.
Yeah. No, we're not dropping the sensor class. We're dropping the sensor prerequisite. Yeah, y'all got me. We're going to drop the prerequisite for sensors off there. We're going to put it back to DC because what happened was the first group that we taught it, we wasn't even teaching sensors. So we waived the sensor class and we brought the class in there and they did just fine. And then the next time we waived sensors, and the next time we taught it 3 times and we waived sensors every time. So if we waived that prerequisite, it means we need to do what? We need to drop it off. Because it's what we call a system troubleshooting level class. Some of y'all had it. Have you had it? Yeah. It's not so we don't teach you how things work. We teach you what they do. So I say I've got this sensor that senses metal. We're not going to try to teach you how it senses metal. We're just going to say it senses metal, right? You understand? So basically, about the only thing you really need to do to take that class is have DC out of the way. Just know how to use meters. So. Well, little mechanics, a little electrical, a little PLCs, just a little bit of that. But we're not teaching it at a level where you would be extremely proficient. So when you get out of that class, you're not going to be able to program a PLC, but you'll know what the PLC does, right? You understand? You get out of that class, you won't be able to fix a motor, but you'll understand what the motor does. So it's going to be a T2 class. I can't remember if it's day or night, guys. So this is where we learn about symbols. And what do we use symbols for? To represent other things, right? So we're going to look at several different drawings in here. By the way, we do teach a class called a blueprint reading. You can't get in it this semester to teach the class because that class is stacked. I mean, it's full. We can't add any more seats. I think we got like 27 people. But language of controls, we're going to look at pictorial drawings, which y'all seen before, electrical symbols and abbreviation, wire diagrams, schematic diagrams, we looked at some of this even in the first chapter, the first lecture. So y'all seen these guys, these are called pictorial diagrams, and what do we do with pictorial diagrams? Yeah, all the components have pictures, right? There is a common symbol. This guy right here, this represents an electrical conductor. By the way, electrical conductors, there are no loops. Every turn you make on a diagram, it's got to be a 90-degree turn, right? You understand that? So this is the pictorial drawing, shows the physical details of the component as seen by the eye. So this is one of the TVs that I got. This is a pictorial drawing. This is what you get normally when you go out and buy a TV or something like that, where they show you the back of the TV, and then they show you how it's laid out. They show you what pictures of devices you can hook up to these different inputs and outputs, right? And this would be a pictorial drawing. So normally pictorial drawing is used for novice people that don't understand the trade, right? So now we have pictures of something. So if you got a symbol for a motor and a motor, they don't even look the same, right? So you're okay on pictorial drawing? Symbols are used to conveniently represent electrical components on electrical electronic diagrams. So it's very important that we learn the symbols of our trade because that's the way our diagrams are going to be drawn. They're going to be drawn with symbols. So symbols take up a lot less space, right? Convey a lot of information to a lot smaller space. So these are some of the symbols we're going to look at. So we already know about the cell. We call them batteries, but technically a cell is just one cell of a battery. And I think I told y'all that. So like D batteries, we call them batteries, but those are not batteries, those are cells. Because to get a battery, it takes at least what? 2. But this is the way you should be drawing a D. Up at the top, you should be drawing that as a D, a C, all those. Now, a cell, I need to bring that over to a 9-volt battery. A 9-volt battery is a battery. It's made of 6 cells. There's 6 cells inside that little rectangular cube thing. And they're hooked in series, 1.5 volts per cell. It's a lead acid or alkaline battery. 6 times 1.5 is 9 volts. So we shouldn't use this symbol, the second symbol down. Of course, I'm pointing and I'm recording. It's not doing good, is it? This is the symbol of a battery, and technically you should have one of these for each cell. So this would be a 3-cell battery if you drew it according to the way it's supposed to be drawn. Now, how much voltage that would be? Well, it depends on what type of battery it is and how many volts you get per cell. Lithium, you can get a lot of those per cell. So you can go out and buy, a 20-volt battery, and if you look at the case, the battery is very low. But if you took that thing and tore it apart, you'd see it's made up of a bunch of little cells that's just connected together, right? Anybody ever took an electric drill battery apart? This is a symbol of an AC voltage source. So this is a symbol of a, by the way, this is a symbol of a DC voltage source also. Get this straight. This is a symbol of a thermocouple. These things right here. A thermocouple is a device that generates a voltage. It actually creates a voltage for heat. And the voltage that it creates would be proportional to the temperature. So we use thermocouples to measure temperature, and they're very accurate. And then they're made out of different metals depending on the temperature range that they have. So you'll see thermocouples. You've got an electric oven. It's going to use a thermocouple in there to do that. Electric water heaters use thermocouples. Then we have what we call a photoconductive cell. Most people call these things photocells. So most people call these are photovoltaic cells. That's the technical name. And most people call these solar cells. And what do those guys do? They create a difference of electrical potential from the energy from sunlight, right? We run into a lot of these. We got originally when the calculators came out, they were big, and they ran off a lot of batteries, and so eventually they went to solar cells to run the calculator. And back then we were using those overhead projectors, and so to see those things you had to do what? Turn off all the lights, and nobody's calculator would work.
I remember that.
Yeah. So these guys would take a flashlight, and when they needed to do some calculations, they'd turn their flashlight on so they could use their calculator. Now we've gone to liquid crystal. Liquid crystal, that's back when we had LED light-emitting diodes that calculated. Now we've gone to liquid crystal. Liquid crystal, those suckers don't pull hardly any current at all. They're very, very low wattage. So now most of our calculators have gone back to batteries. Still, they last for a long time. Conductors, this is where people get into problems. Conductors, usually the thicker the line, it usually means it carries more current. And of course, if I don't put a dot, what does that mean? It's not connected. So to show a connection, you got to have a dot. This is a symbol of a true earth ground. Then we have our switches. That top one is not a normal symbol that we use. For that switch, if you looked inside the switch, this is a symbol. Normally we use a symbol. Most of your industrial contacts, our switches are what we call double break. So normally if you looked in a light switch, or what they call a snap switch or a wall switch, it should be drawn as this symbol right here. Now a double switch, a double contact, which would be this. Now we use a lot of double contact switches or push buttons in industry. So what advantage does these guys have over that guy? Well, one of the problems that we have in industry every once in a while is we'll get where a contact welds together. Which means when it comes down, every time a switch closes, it creates an arc, and every time it breaks, it creates an arc. And those arcs are 32,000 degrees. So we try to break real fast and try to bring them together real fast because that helps extinguish the arc. But sometimes what happens is the contact will actually, we call it a welded contact, where the actual contact gets welded over to the other side. Well, the advantage of a double break, you've got two chances of breaking the circuit. And plus the way the double break works, it's on a tilt. So if this one breaks loose, it'll come up, and that'll automatically almost always break the other contact. So these double break contacts. These are less susceptible to welding together. So most of your relays have double break contacts. Not all of them, but a lot of them have double. these little control relays that we'll be using. These are not double plate contacts. Then we have our limit switches. Now, let's see if I can find a couple of them. Limit switches have been around for a long time. I talked to somebody about it. Now these guys come in different shapes, well not shapes, they come in different sizes, depending on how much current they've got to carry, and then how much voltage they got to break. So we got this voltage that's pushing, right? It's pushing all the time. It's doing all it can to try to cause current to move. And the higher the voltage you have, the more push you have. So usually when we get into contacts or things that's supposed to break a circuit, they're going to be rated in two things. So most of our electrical or electronic components are rated in at least two different things. So like a resistor, what's the two things that our resistors are rated in?
Ohms and reactance.
Resistors don't have reactance.
I mean, reactance.
Ohms and watts. Actually three things. Ohms, watts, and then we have a tolerance, right? I think y'all probably told you this class, some of y'all this class, we used to teach a class where students would design and build their own power supply. And then when they got through with the project, they were supposed to create the specs on the thing. And they'd come in there and they'd say, something's wrong with my power supply, it keeps burning up resistors. Because they were looking for they was looking for a 100 ohm resistor. What they didn't pay any attention to was their power supplies put over 15 watts out. 15 volts out. So B squared over R, right? So that'd be 15 squared over 100 ohms. How many watts is that? So what was they doing is that it wasn't nothing wrong with their power supplies, that when they went and got their resistors, they didn't pay any attention to the wattage. They just said, I need a 100 ohm resistor. So this is a limit switch. So these are mechanical devices. And it has this thing right here called an operator. And then what happens is that when it comes up and hears something, you hear it click. And you hear it click because what it tries to do is make these contacts open and close real fast. So this has one set of normally, this is not the right symbol, by the way. It has one set of normally open contacts and one set of normally closed contacts. And then this shows me the manufacturer numbers. Now what they've done, so manufacturer numbers, these are the numbers that electricians would use to know how to wire things up, right? Understand? So what they've done on ours is they brought these manufacturer numbers out to these terminals right here. So instead of me coming here and taking off this cover and then sticking it through this hole down here and wiring it up to these different terminals, then we can wire them up right here. So it means between 1 and 2, I have a normally open contact, and between 1 and 3, I have a normally closed. So if I was to take my ohm meter and put it between 1 and 2, right now it would measure really low ohms, right? You understand that? And then 3 and 4 would measure infinity or overload on your meter. But if I was to come up here and do this, then what's going to happen? Well, now 1 and 2 is going to close, and 3 and 4 is going to open, right? You understand that? Now the problem is that the piece of equipment that I'm working with, when it's at its rest position, it might be sitting like this. So when we draw these symbols, we draw these symbols at the position, at the neutral position for the piece of equipment. So that means right now, my normally closed would be held open, and my normally open would be held closed. That makes sense? Everybody follow that? Because this is where the piece of equipment is sitting there when it's at rest, or when I hit a reset or whatever. So we have 4 symbols that we use for these relays. And what you do is you look and see what gravity is trying to do. So gravity, so what's gravity trying to do? Well, gravity is trying to close it, right? You understand? Everybody understand? Yes. What's gravity trying to do with this one? It's trying to close it, so it must be held open. Right? You understand that? Now look at our normally open. So gravity's trying to open it. If I look at this, it's on the bottom of the dot, right? You understand? Gravity's trying to open it, so it must be what? It must be held closed. So here's our 4 symbols for freedom. So the contact for a limit switch, we start off with our terminals right here, which should be open, right? So they should be open like this. That indicates we got a connection point. And if I come over here and do what? If I come over here and do it this, here I'm drawing it to the top, then we put this little incline right here. I guess that would be a decline, right? And it should touch, then this would be normally closed. Because gravity's trying to close it, and it is closed, right? I don't know any other way to teach that. Here, gravity's trying to close it, so something must be doing what? Holding it open. So this is the symbol of a limit switch. Right? This is the symbol of the contact controlled by the limit switch. And we have different operators. We got all kind of operators. This would be what they call, this is a heavy duty. This guy here is rated at I don't see it. The series A1. I was trying to see the rating on the contact. Everybody okay? Let's go ahead. So when y'all draw your drawings, and you're going to have to do, especially if you take the sensors class. In the sensor class, guys, a lot of the labs that you do in there, you actually design yourself. So, and it's basically, the sensors class is a continuation of this course. So that's why you have to have, it's just more advanced. We get into a little design. We let you design circuits. Your team design circuits. Of course, you always bring them up to me and let me look at them to see if it works. So here's our symbols for our motors. So a single phase motor. The second one is a dual speed motor, 2-speed motor. So notice here we have low, high. We have a 3-speed motor up here. We have the frame for the armature for a 3-speed motor. I'm sorry, the stator. So it would have another lead. You'll run into these in air conditioning systems, then a 3-phase motor. Now, when we get into motors, we'll talk a little bit about delta Y. The symbol itself does not identify whether it's a delta motor or a Y motor, unless they draw the little symbol right here. Delta Y motors, if you have a delta Y motor, it really don't make any difference if that's all it does. It's when you get into these multi-voltage motors where delta Y makes a difference. So normally, what they'll do is they'll start motor Y and then they'll switch over to delta when it gets up to a certain speed. We'll talk about that. This is the symbol of a solenoid. We've already seen solenoids, right? You okay there? This is the symbol for a fuse. We've already looked at that. This is the symbol for a circuit breaker, but it's usually arc with a ball.
So the fuse can be drawn that way or the other?
Yes, this is the international symbol. This is perfect. So you'll see sometimes it's drawn like this.
I'm talking about the other. So we seen it. It was.
This is the actual ANSI symbol for fuse.
Okay, let's flip the other way. Yeah.
Okay.
As long as it's curved like that.
As long as it's curved like this, fuses can be mounted different ways, right? So it doesn't make any difference. Well, I understand. Yeah, it don't have to be drawn. In fact, this is what this is. This is the disconnect. So disconnect is something we can use to. This is where your lockout will be at. Usually, it's on your disconnect.
A lot of them nowadays have those where you can actually insert the lock into.
Yeah, this one has the lock. It's got the tabs over here on the right hand side. Your big disconnects are still going to have a handle on them. Some of them have push buttons on, by the way. So ours is a push button disconnect. So it's got a relay inside there. And when you push that in, it energizes that relay. So that's why ours is so small.
Some of our stuff historically, similar like those, he hardwired them in to where you get that e-stop, you have to come and unlock it or power it.
Yeah, you can buy e-stops. Ours are not what we call latching e-stops. So we have latching e-stops, which means once you push them in, you literally got to push them back in some and then turn them and bring them out. And you that exactly that. So ours is sort of like the ones you got. So once you hit that e-stop, you can pull them in and out all day long. Nothing's going to happen until I come over there and hit that key. So it sounds like those disconnects are like y'all.
Yeah.
We don't have a bladed disconnect. We have a relay disconnect. So there's a relay up here. But ours are fused. And the fuses are exactly what they're showing. So we have 3 fuses inside our disconnect. And we're going to make measurements inside our disconnect. We're going to simulate an open inside our disconnect. We're going to do this stuff in there. We'll get to see the actual relay and stuff. Are we okay? Huh? This is a diagram. I'm going to show y'all a true. This is what they call a wiring diagram. Now, in control circuits, we usually have 2 sections. We have what we call the control circuit, and this is going to be low voltage. And then we're going to have a power circuit. So the control circuit is going to control the power, right? You understand? So this will be control. This is very common. And that'll be power. Your control is going to be at a low voltage. Considered, ours is going to be 220. And then this over on your power, this will probably be a high voltage. So your power circuit is usually really isolated. This is the one that's going to be inside these cabinets. It's going to be locks, tags, and all that kind of stuff because that's got a voltage high enough to kill you, right? You understand? Your control circuit is going to be usually drawn. The control circuit is usually, we'll draw our control circuit using a ladder diagram, but normally your power circuit is going to be a wiring diagram. So what a wiring diagram tries to show you is the relationship between the different components inside a circuit. So notice this line right here that goes between dots and dashes and dots and dashes. What this means is that these guys here are physically mounted together. They're usually inside the same enclosure. And they try to draw it so it kind of gives you an idea of how the parts are oriented within a system. So this is the wiring diagram. The wiring diagrams, the location of the component is generally shown as close to the actual circuit configuration as possible. So this is actually a wiring diagram for HVAC. So we know that all these are mounted what? Together. We know all these are mounted together. We know all these are mounted together. And then of course we have the way they're connected. So this is the wiring diagram. So what a wiring diagram tries to show you, it uses symbols, but it tries to draw those symbols on how the components are related to each other, which makes it hard to figure out logically. So this is hard to trace. It would be a little hard for me to try to figure out the actual circuit, right? Understand? This is where you get your colored pencils out and you start tracing colors. Okay? This is a schematic, and this is not really a schematic. Doesn't care how things are laid out. It's going to try to show you how logically the circuit works, a sequence of events. Inputs on the left, outputs on the right. No matter how they're laid out, no matter where they're located, inputs on the left, outputs on the right. So schematics are drawn from left to right over in the good old United States. Some German prints were drawn from right to left. But still, it would be for that country, right? Which is pretty one. We got some German equipment out of U.S. Steel. We had to redraw the schematics on it, so it would be hard for us to do that. So this is a schematic. Schematic diagram components are laid out so the circuit is easily read rather than to show the actual position of the component. And normally, guys, we don't draw this wire right here. Very seldom anymore do we draw this wire. We represent it with a symbol. So normally what we do is this wire is not drawn hardly any time anywhere anymore. And we would represent this with a symbol. Normally it's going to be a ground even if it's not grounded. Now what that symbol is, what that's telling me is there is a wire there. There is a conductor, but what I'm doing now is I'm representing that conductor with a symbol. And that what that means is that's going to be one less wire I'm going to have to draw inside my schematic. And every time you leave off a wire, the schematic gets a little easier to read. So this is a schematic for a power amplifier. But I know my inputs are over here. Here's my input would come in. And this whole thing does what? Flows this way, and here's my output. And these are the guys that's actually driving the thing. But it don't make any sense unless I know what all these symbols are, right? But if I learn these symbols, then it would make a sense. That makes sense. So these are NPN transistors. That's a Zener diode. So this makes sense to me, right? That's a capacitor. This makes sense to me because I understand it. But notice it's not. We don't know. These guys might be. One might be here. One might be there. One might be here. They might be mounted on the same unit. They might not be mounted. We're not concerned on how it mounts. We're concerned on how the dang thing operates. So a schematic doesn't. I'm looking at a schematic. R1 might be here and R2 might be way down here. And the schematic, they're going to be drawn right next to each other, positive, right? You understand? When I lay these things out, I'm going to try to lay them out so I can make it as small as I possibly can make it and without any crossing lines. So these things get kind of weird. You'll find yourself looking all over the place for R1. And on your schematic, it's going to be up here somewhere, right? Except they didn't label the R's on this side. They just gave us the values. A ladder diagram. So this is what we're going to do. Also called a line diagram. So those two terms are interchangeable. A diagram consists of a series of symbols connected by lines that are laid out like a rungs on a ladder. That indicates the flow of current through the various components. So what we do is we have two power rails. It's coming up here next, but I'm going to draw it anyway. That generically we call L1 and L2. We're going to call ours CL1 and CL2. Now, why we're going to do that is because the three-phase is called L1, L2, L3. But we're not going to connect to L1, L2, L3, which is three-phase, over 200 volts. We're going to go through a transformer. So technically, I don't want to call it L1 and L2 on the bottom of the transistor, so we're going to call it control L1 and control L2. And then we build circuits between L1 and L2. L1 is considered to be the power, or in electricians would call this the hot lead, and then L2 is considered to be the common, or what electricians would call the neutral, which is the return conductor and which is the source conductor. Well, in DC, L1 could be negative and L2 could be positive. Right? Understand that? Or L1 could be positive and L2 depends on what system I'm wired up and what my loads need. Right? Understand that? In AC, there's no such thing as a return and a source conductor because they're constantly what? They constantly change. Of course, we're going to be dealing with AC. And then we'll build a circuit between here. This is another variation of the memory circuit. And we give this is a relay. I need to bring that down. This is a symbol for a relay, right? Of course, the lines don't go in there. And then I'm going to give the relay a name. And then I'm gonna come over here and put this. The contact that I label, if I give it the same name, it means that this contact is being controlled by that relay cord. Is everybody okay there? Yes or no? Makes sense? In Germany, they like to put, and then we label our switches too. We can call this run and maybe stop or whatever it is. We might call it up, right? You understand that? Those are push buttons. Momentary contact push buttons. Now that would be one circuit. And then I could come down here and do what? Put another circuit, right? You understand that? What's this? What's that a symbol for? No, a resistor would be at least 5. So that's a resistor. Symbol. Solenoid. What's a solenoid? We've already showed y'all that, guys. What's a solenoid? It's an actuator. It's a linear actuator. An actuator is a device that takes a power source and converts it into motion. Linear means it moves in a straight line, so a solenoid is a linear actuator. We can't have relays without solenoid. We can have a solenoid without a relay, but we can't have a relay without a solenoid. I don't know what this solenoid is rated at. These things come in all shapes and sizes, but this is a solenoid right here. And that would be the symbol I would represent that. Sorry. So what happens is when I put power on this thing, and I didn't bring any dang jumper in here. Let's see if we can make it work. I think it's 12 volts. Look at that. Got 9 volts. Oh, wait a minute. Turn it off, Rich. Got too many wires up here. I don't know if I can get this. I can move the camera. So this is a solenoid. So what I do is when I put current through here, it creates a magnetic field. You know, I showed y'all the straw with the nail in it. Didn't I show y'all that? Say yes. That's what a solenoid does.
Can't see it.
You got a magnet against this roof?
Huh?
You got a magnet against it?
No, I got an electromagnet. Now, what advantage does an electromagnet have over a regular magnet? We can turn it on and off, and we can control its strength. So what happens is when I come over here and put current flow through that coil of wire, there's a bunch of coils of wire creates a magnetic field, and it sucks this armature up into the solenoid. Now that's the solenoid, right? That's it working. Now what I have to do on this one, this is what we call gravity return. So I'm gonna have to lean this one down. I could put a spring on it, right? You understand? So that's the solenoid. It's a linear actuator. Well, that's the solenoid itself, but inside my diagram, I would do it with that two things. It's not a resistor. You'd have to do more than two crooked lines to get a resistor, right? Usually 4 or 5, right? 4, I think, is standard. This has only got one up and one down. As soon as you go up again, it's no longer the symbol of a solenoid. Where do we use solenoids for? Have anybody ever been buzzed in before? What's actually unlocking the door? A solenoid, right? Anybody got an ice maker in their refrigerator? What turns that water off and on? Solenoid. There's a solenoid that's got a blockage in it, drops down, turns the water off. You hit that thing, turns it on, lets the water. Anybody got a wash machine in their house? What turns on the hot water? What turns on the cold water? You know, what does that? Solenoid. So solenoids are just linear actuators, anything that we want to do. Now what we do is we take this solenoid and we put contacts on this outside air. Now all of a sudden we got a relay. So a relay is just nothing but a solenoid that's got contacts out there, and this plunger opens and closes contacts. So a relay, what advantage does a relay have over a regular manual operated switch? It's electrically operated, right? You understand? So now I can turn it over to automation. So I can't have manual devices. Couldn't you imagine down there at Mercedes of every pneumatic valve, when they moved that thing, somebody had to go over there and flip a switch? They'd have 15,000 people over there, right? You understand? Running all over everybody. Okay, now, instead of having robots, right? You understand that? Yeah. All right. So all a relay is a solenoid with contact, controls contact. And of course we get a different symbol. But that's the symbol of a solenoid right there. It's a load, it's an actuator. Yeah, it's a load. It's not a control device, it is a load. But as soon as I put contacts on it, we get a different symbol. Right? You understand? So when I put a contact on it, we represent the coil. We represent the coil is that right there. That's the coil to the solenoid right there. But it's the coil, it's the contacts to the solenoid, but we call it a relay because it's controlling what? It's controlling contact. But every relay has some form of solenoid on it. Well, that one up there, you can actually see it. It's like this. It's got the solenoid down here, and then it's got a magnet right there. And then it's got a wiper on it. It's got a spring on it that basically comes over here. And when we turn on the solenoid, what does it do? Pulls it down, it's got a spring on it, and it pops it back up. That's a relay too. So that's the symbol of a solenoid. So here's the ladder diagram. I almost have this one wired up over there, but I didn't use a motor starter. So this contains two circuits. So a rung is a circuit that runs between L1 and L2. So we have two circuits. We have the one on the top, and then we have the one down here, right? The second circuit is controlled by the first circuit. Well, I'm using a control relay. I'm not using what we call a motor starter, so I don't have the overloads up there. So this is the circuit I've got right here, and I'm using a control relay. What we have there, this is what we call a memory circuit. We run into that a lot. It allows us to control a circuit with push buttons and set switches. So now we have what we call a push button station where the operator just goes up and pushes buttons. They can do those with the gloves on, right? Understand, it makes it very easy to operate. So how does this operate? We've seen it several times. But right now, the way it's drawn, so it's drawn in its off position. What do I need to do? So we got energy sitting where? We got energy sitting right here. It's coming down here, it's sitting right there, but it's got nowhere to go. This guy's coming flying through. That's a normally closed contact, so it comes through. And we got both wires now. We got both L1 and L2 connected across the light, so the light should be on, right? Everybody understand that? So what do? Just touch the start button. As soon as I push it in, it's gonna come in. Now we got power across our relay. The relay energizes. This contact closed. We pick up a secondary path. So what can we do now? Yeah, we can let go of that guy, and it stays sealed in. Like I said, some people call this a memory circuit. I lost my color. Until I do what? So now that's going to come up here and open this contact. So it's going to open up. Just put a circle around it. Now the energy stops right there and the light should go off. So when I come over there and put power on this circuit over there that's wired up, then we should see the light come on instantly, right? You understand that?